In this lesson, we're going to be learning about fields. More precisely, we're going to be learning about electric fields. But before we get into electric fields, we're going to be reviewing about some fields that we learned in Physics 20. We're also going to look at some situations on where fields have affected us. So we're going to start off here by looking at experiences that we have all come across of where objects at a distance affect or move other objects depending on their proximity or distance proximity. So let's take a look at this snowman here. As the snowman moves closer to this Bunsen burner on this side, what's going to happen? He's going to melt faster. There is a heat that affects the snowman and he will melt faster. There is a field here that is affecting the snowman. The temperature is greater as we move the snowman closer to the Bunsen burner. So what is a field? A field is a region of influence around an object. So let's review how the field of this flame affects the snowman. So first of all, we know heat radiates off an object. So in that case, if I look at this here, heat's radiating, which means it comes from the center perpendicular to the surface of the object out. So I want to make radiating rays from my flame. Now, if I was to move my snowman closer, these rays hit him. But now look what happens. As he gets closer and closer and closer, more of the rays hit him because they spread out. So eventually what happens is, as more of these rays hit him that are radiating out, more of the field is going to influence him. So he's going to feel more temperature, which means he's going to melt faster. As he gets closer to my field, as the proximity decreases, our snowman is going to start melting. If we remember from 2 videos back, we learned that gravitational laws and Coulombs law were very much related. They're very similar in many ways. So to help us understand electric fields, we're going to first look at something we learned in Physics 20. We're going to look at and review gravitational fields. Now, if we remember, a gravitational field of an object is related to its mass and the proximity from it. So let's take a look here at a spaceship and the Earth. So we're looking at the gravitational field of the Earth. And then we have a spaceship coming near it. So as my spaceship comes closer to the Earth, what's going to happen is our gravitational field strength is going to increase. So the proximity of the shuttle to the Earth determines how strong or how much the gravitational field is interacting with it. We learned later in that unit in Physics 20 how we could then use that gravitational field strength to help the rocket stay in orbit, or spacecraft stay in orbit around the Earth. So another thing we learned in Physics 20 is how we could use those gravitational fields to our benefits when sending probes from planet to planet. We aim them at one planet and we'll put it so it interacts with this gravitational field and bends around it and then releases at a certain time to go to another planet. So with that in mind, let's take a look now at electric fields. So just like gravity in Physics 20, when we look at electricity and a charge, it has the same ability to affect objects at a great distance. For instance, when I put this charged balloon near this electroscope, what's going to end up happening is the needle is going to move away. It causes this needle to move. Another example, there are many objects that can create electric fields. For instance, this Van de Graaff generator here could create its own electric field. Or how we learned in the video before, using the triboelectric series, how by rubbing certain objects together, we'll gain or lose electrons, making them get a charge and thus an electric field. And these things that produce electric fields may influence or affect many things within proximity, such as hair, water, and electroscopes. In this picture, I have a Van de Graaff generator which is creating an electric field, and I have this pith ball or a ball being influenced by that electric field. I have another picture here where I have myself and I rub this balloon against my hair, and depending on where the proximity of the ball is to my hair is affected by the electric field. Notice as I get closer, as the proximity decreases, the strength of the electric field increases. So our field types could be divided into 2 categories, either scalar or vector. Scalar quantities do not depend on direction. An example of this would be like the snowman with the Bunsen burner, which is a heat field. Right here, there is no movement. It is just the proximity towards, or proximity of the heat field determines how hot it is. Another one is a sound field. So the closer you are to it, the louder it is. The second class is the vector ones, which depends on direction. Think of these ones as having a pole. So if there's gravitational forces, they're going to pull each other together. Now we looked at electric forces. So with electric fields, sometimes they're going to repel, sometimes they're going to attract. Same with magnetic fields. We learned that two like magnetic fields are going to repel. You learned that in science classes before. And opposites will attract, just like electric charges. So we have to now look at some definitions here. So my first definition is going to be something called a test charge. A test charge is a very small charged object, which doesn't influence what something is going to be called our source charge, like over here is my source charge. So if I look at this here, I have a test charge of a positive and a source charge of a negative. My source charge is going to be the thing producing an electric field. In this case, both of these are opposite charges, so that means the positive is going to be attracted to the negative. So the test charge has a very small charge, but its field isn't big enough to affect my source charge's field. Here's another example where we have a source charge here that's positive and my test charge positive. The test charge is going to be moving away because opposites repel. And that gives an example of why these are vectors. There's movement involved. So now, based on what you learned about gravitational fields and forces, and also about that heat field in our first example, I want you to look at this diagram here. And I want you to say, for these 2 point charges, what the electrical field difference will be between point charge 1 and point charge 2. And how are these vectors represented? And why are they going in that direction? If you look, there's some differences between these vectors. There are different sizes, and the direction is different. When I was to move that snowman, there was no direction, but the strength of it, the magnitude, mattered. Here, I have 2 different things. I want you to be able to try and explain why. Now think of that using maybe gravitational forces or gravitational fields to help you. So now pause the video and show me your answer for this in class tomorrow. So let's look at the directions of electric field lines. We're going to start by looking at positive. I always want you, when you're thinking of this, just to memorize the positive, and we know the negative is going to be the opposite. So the positive charge is kind of like the sun. Everything is radiating out, just like heat. So here, my field lines are moving out away from the center. As I get closer to my charge, or the center of my charge, if we notice, my field lines are closer together. So that means the electric field strength there must be stronger than way out here, just like gravity. Now that we know the positive, let's look at the negative charge. The negative charge is just the opposite. Everything is coming in. As we get closer to my charge, the field lines come closer together because they must be perpendicular to the surface. So what happens when a positive interacts with a positive? Well, both of them are moving away, and field lines cannot cross each other. That's a key thing. Field lines cannot cross each other. So they're going to bend away from each other and repel. So if I had 2 negative charges, my diagram would look identically the same, except my field lines would be going towards the charges. Everything would bend away like this, but they would be going towards the charges. Now let's take a look what happens when I have a positive and a negative. When I have a positive and a negative, everything's going to go from the positive towards the negative. And notice right here in the center, in between them, how the field lines are, how close they are together. What does that mean? Now that we know what electric fields are, and we reviewed fields in general, we're going to now calculate quantitatively the strengths of electric fields and how they impact certain objects. Now if we remember, electric forces and gravitational forces are very much related, how they are set up. So we also learned earlier that electric fields and gravitational fields are somewhat related as well in how they interact with objects. So then it would go to reason that a gravitational field would be somewhat similar how we calculate it as an electric field. And that is true. If you remember, a gravitational field is the field between two masses. Well, all we did to figure out the field was we just did the force divided by the one mass of our test mass. In this case, we're going to be looking at the electric force from Coulombs' law and divide it by our charge of our test charge to figure out the field. So it's very similar. So once again, here we have my electric field is equal to my electric force, which we could find through Coulombs' law, divided by my charge. And the symbol for a field is normally held by two bars like that. So the definition is force per unit charge. So if I want to know the force per unit charge, that is the exact same thing as my electric field strength, because we have force divided by charge. So force per unit charge. So my units for electric field strength is going to be newtons per coulomb. Now that we know our theory and formula, let's do some calculations. One key thing is to note and remember, a point charge is just a positive or negative point in space. The amount of positive and the amount of negative is always going to be measured in coulombs. We're going to be doing a lot of calculations with fields involving alpha particles, protons, and electrons. Here are some values that it will be given to you on your diploma and in your formula sheet, but you should try and memorize. One thing I want you to take note, maybe think about it now, why do you think the charge of an alpha particle is double that of a proton? But yet if we look at the mass, it's 4 times the amount approximately. So what do you think is an alpha particle? Let's take a look at my first example. I have a sphere with a negative charge of 2.1 times 10 to the negative 6 coulombs experiences an electrostatic force repulsion of 5.6 times 10 to the negative 2 newtons when it is placed in an electric field produced by a source charge. Determine the magnitude of the electric field and the source produced at the sphere. So to start off here, I know that my charge is 2.1 times 10 to the negative 6 coulombs. We know my force is equal to 5.6 times 10 to the negative 2 newtons. And we're trying to figure out what is my electric field. So we're going to use the formula. My electric field is equal to force divided by charge. So I'm going to end up getting 5.6 times 10 to the negative 2 newtons divided by 2.1 times 10 to the negative 6 coulombs, which will end up giving me a total of 2.67 times 10 to the 4 newtons per coulomb. So let's take a look at example 2. Here we're trying to figure out my electric field strength. And it is an electric field strength on a proton, which we know the charge is 1.67 times 10 to the negative 19 coulombs. And we know the force applied to that proton from the electric field is 5.3 times 10 to the negative 2 newtons. So if we're trying to find my electric field strength, we know my electric field strength is equal to my force, electric force, divided by my charge. My electric force in this case is 5.3 times 10 to the negative 2 newtons. And my charge is 1.67 times 10 to the negative 19 coulombs. That's going to give me a total of, or electric field strength of 3.17 times 10 to the 17 newtons per coulomb. So far we only did questions that involved an electrostatic force and a charge, and we know electrostatic force divided by charge is equal to my electric field. But you might be thinking, wait a minute, from the beginning of class we learned that 2 of the most influencing factors is going to be the charge of my source, not necessarily my particle or my point charge, but the charge of the source and the distance between my point charge and my source charge. Those are huge influencing factors in fields. So then, how do I use these quantitatively to solve more in-depth problems? Like, we know my field strength will change as we change proximity from my point source and my field source. Well, we're going to figure that out here. And we're going to use skills that we developed in Physics 20. Remember when we looked at gravity and gravitational fields, and we looked at the force of gravity, we were able to put in, since we know the force of gravity is used to calculate gravitational fields, we're able to put in the equation for the force of gravity into my gravitational fields equation. Just like what we're going to do here. So we have my electric field strength is equal to the electrostatic force divided by my point charge. Not the source charge, but my point charge. We know that my electrostatic force, due to Coulombs' law, is equal to Coulombs' constant multiplied by my two charges divided by the radius squared. So then if I substitute my equation for electrostatic force into for electrostatic force, I'm going to get something that looks like this. And here we notice my charges, my point charges, cancel off. So the only thing we need in this equation, we just alter the equation, is we could say the electric field is equal to Coulombs constant multiplied by my source charge now divided by the radius squared. My last question is going to apply everything we learned so far in this video. We're going to apply or use the theory we learned about fields at the beginning, and we're going to be looking at some quantitative calculations that we learned in the second half of the video. So let's start here. A proton and electron are separated by 50 centimeters. Calculate the electric field strength and direction midway between them. So I'm looking at a point charge midway between. I want to figure out the field strength. Before we get there, let's think about what's happening here. Let's draw my field lines. So if you remember, my field lines always go from a positive to a negative, like so. And they're going to be very tight together across here. They always come off perpendicular, kind of like this. And remember, to a negative, it's always coming inwards to the negative. So I'm going to get something that looks like that for field lines. If I look in the middle here, my field lines are very much close together. This point charge is going to be affected by both source charges of the proton and the source charge of the electron. So I'm going to have to add both of those charges together to figure out what is the field strength. So since my point charge is in between two source charges, and I want to figure out the influence of both of those source charges, I'm going to have to find the sum of both source charges on my point charge. So let's look at what we know. I know my radius is equal to 25 centimeters, okay, because it's right in the middle. I know my charge of the proton is 1.67 times 10 to the negative 19 coulombs. I know the charge of an electron is 1.67 times 10 to the negative 19 coulombs. And I know Coulombs constant is 8.99 times 10 to the 9 newtons meters squared over Coulomb squared. So let's put in my equation here. I know that my electric field strength is equal to Coulomb's constant multiplied by my source charge divided by my radius squared. That's going to give me 8.99 times 10 to the 9 multiplied by 1.67 times 10 to the negative 19 divided by 0.25 squared. When I put this in my calculator, I'm going to end up getting 2.4 times 10 to the negative 8 newtons per coulomb. Now, I know that the electron and the proton have the exact same charge, and they're going in the exact same direction in this case, and we also know that the distance between them is the same. The field strength applied in that position from both of them are going to be identical, so all I have to do is now double my field strength to get me 4.8 times 10 to the negative 8 newtons per coulomb. Now, one thing we have to remember is that this is a vector, so I have to put in which direction, and this is going to be to the right. And that's it.